So we've just focused on ax plus b all to the power of n. But what happens if we generalize this? So it's not just something of the form ax plus b in the brackets, but rather it's just some general function of x that is now to the power of n. So the same thing applies if we start with differentiation and we just focus on what happens when we differentiate this again. Using the chain rule, we can focus on inside the brackets. So that's our dib, differentiate inside the brackets, and then we differentiate outside of the brackets. So if we were to derive this function, or this composite function, differentiating inside the brackets. So what is the derivative of fx? Well, since it's so general, we're just going to call it f dash x, right? The first derivative of fx. So there is our dib. We've differentiated inside the brackets. Now we need to focus on the outside of the brackets and just almost pretend like this whole thing is just an x. So it's x to the power of n. So the n comes out the front. Then we have our brackets still remaining the same. And then we reduce our power by 1. So this would be our chain rule derivative of y equals fx to the power of n. Keeping this in mind is really helpful when we move to our integration and we're actually seeking to sort of undo these kind of things, or look out for any functions of x where we can actually see something that might look like their derivative attached to it as well. So it's important to recognize that. So let's go and set this up nicely now. The chain rule for something of the form f dash x times fx to the n. So if we have an integral and we notice, okay, there's some function of x raised to a power. And looking at this inner function of x, we see that the derivative of that is also attached. If we see this form of integral, then we can follow the chain rule, where we say, okay, we're going to raise the power. So we've got fx, and we're integrating, so we raise the power by 1, so it's n plus 1. But then we need to put it over n plus 1, right, to compensate. So remember, going the other way, when we derive, the n plus 1 comes out the front and it will cancel with this n plus 1 down the bottom. Our power will drop by 1, and so we'll have fx to the power of n, which is really good because that's what's in the original integral. But what about this f dash x? Well, unlike the last video, we actually don't need to do anything more. There's nothing, we want the f dash x here. So when we fully derive this and we do the dib, the differentiate inside the brackets, f dash x will come out the front, and that's exactly what we want. Right, so we can't get rid of it or anything like that. As well as the fact that it is a function of x, it's not just a constant, so we can't get rid of it, but we don't want to get rid of it, it's right here. So this is good. The only thing we've got to do is just put our plus c, our constant of integration, and also for this we'll once again state that this applies to all the cases for n except for where n is -1, because we can't have n being -1 down here, because then we would get 0 on the denominator. So the key thing that I want you to look at is when you see an integral and you notice some function of x to the power of n, and then if you derive that function and you see its derivative attached, then you know we've got a chain rule that we can use. So let's do our first of two examples now. We have the integral of x outside of x squared plus 1 all cubed. So we're going to do a little bit of preliminary working out to set this question up, because that can be really helpful if we just break it down into parts. So comparing this example here to this more general rule that we have above, what's sort of the little function of x that we might focus on first? What's the function that's been raised to a power? It's here, x squared plus 1. So if we set this up as our little function of x, we can say, okay, f of x is x squared plus 1. This is the function of x that's been raised to a power, in this case 3. Now what's the derivative of this f of x? So what's f dash x? Right, because we want an f dash x as well. So x squared plus 1, when we derive it, we get 2x. Now, is there anything else in this question that looks like a 2x? Well, we've got an x here, so it's not exactly a 2x. You know, if there was a 2 here already, that'd be sweet, but there's not. But the only difference is the constant 2, and constants, we can deal with them very easily. So because we would want a 2x, what I would encourage you to do is to set it up so that you get exactly what you want. So we're going to rewrite this integral, and instead of x, we're actually going to put 2x. And then we have our x squared plus 1 all cubed. But I can't just do that, can I? Just put a 2 in randomly, because that changes the question. And you're right, we can't just add a 2 in, so we need to counteract that. So when I multiply something by 2, like I've done here, to counteract it, I would also multiply by a half. And I'm going to put that half out the front of the integral. Right, so look at this now. 1/2 times 2, it's actually as if nothing's changed. So it's still the same integral, but now it looks a bit different. And we've done that so that we introduce f dash x into our question. All that's left to do is to apply the rule from above. So we're going to raise the power by 1 and put it over the power. And yeah, we've just got to remember we've got this half out the front. So let's give ourselves a bit more room. And here we go. So we have our half, and then our integral. I'm going to use big square brackets here, even though it's not a definite integral. Okay. We have our f of x, so x squared plus 1. We're raising the power by 1, and we're putting it over that power. Simple. Remember, we don't need to compensate with this first derivative. Okay. And then we put our constant of integration on the end. So the last thing that's left to do is just tidy this up a little bit with the fractions. So the 2 on the denominator and the 4 on the denominator, we could combine them and turn it into 8 on the denominator. And that's our answer for example 1. Let's do one more example. We have the integral of x squared times the square root of x cubed minus 1. So, what might we do? Well, hopefully you remember that it's very beneficial for us to change our radical signs into fractional indices. So let's write this square root as power of a half. And now we say, okay, I've got some little function of x here raised to a power. So my f of x within the question is x cubed minus 1. What's the derivative of this? F dash x is 3x squared. We just have an x squared in our question though. So the next step, before we actually get on to solving the integral, is to make our question look like this 3x squared, right? We want it to be in the form that's best for us. So we want a 3x squared instead of an x squared. But if I'm going to times by 3, I need to compensate and times by a third. Okay, so we'll chuck that third out the front of the integral. Constants, right? Constant values can be brought out the front of integrals, not anything else. No x values or anything like that. Okay, so this is still the same integral, right? So everything you see here is the same in each of these three places, but it just looks different, and it's a little bit nicer for us to apply our rule. So we have 1/3, and now we're going to follow the rule. We say here's my fx, so my x cubed minus 1. I'm integrating, so I raise the power by 1. So a half plus 1 is 3 on 2, and then I put it over that new power. Constant of integration, don't forget that. And now we just need to tidy up. So what's going to happen with our fractions? Well, this will become 2/3, right? So we can flip the fraction. So we'll have a 2 coming up the top of the fraction, the 3 will remain on the bottom. So the 2 is up here. The 3 goes down the bottom. However, we've got this 3 as well. We've got the 1/3 out the front, remember? So 3 times 3 gives us 9. Now, once again, you know I like to change it back to this form. Okay, so we could change it back to radical form, but for this one I am just going to leave it, and if you would like to change it back, you can do that yourself. Okay, so that finishes off our second example for this second video of chain rule. Good job, and all the best with the exercise.